Hello everyone. In today's lecture, we'll be discussing how we can find a suitable Lyapunov function which can provide the maximum region of stability. And also we have example to validate this concept. So what you have understood from the last lecture that if you have a positive different function, which is basically Lyapunov function, and p dot of x, if it is negative definite or negative semi-definite, we can comment on the stability of the system without solving the dynamics. Now the question is how we can find this positive definite function which can provide us the maximum region of stability. So the concern is how we can find the positive definite function which can provide the maximum region of stability. So here we are going to consider the Krasovsky theorem, that is a very important theorem in nonlinear control synthesis. So here, through which we can find the Lyapunov function, which can provide the maximum region of stability. So theorem is Krasovsky theorem. So here, let me first state the concept, then we'll have the example. It provides a sufficient condition for asymptotic stability of an equilibrium point by constructing a Lyapunov function based on the system dynamics. So for example, let us consider you have a system. Consider a nonlinear system x dot equal to fx, where x is the dimension of x is n, and f of x is a continuously differentiable function. Also assume f0 equal to 0, meaning that origin is an equilibrium point. is an equilibrium point. Okay, so here from this system, this system is defined by equation number 1. So we can form a Jacobian matrix of the system. The Jacobian matrix we can form f of x, capital F of x, equal to dou f1, the partial derivative of function f1 with respect to x1, dou f1 dou x2 dot 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 dou fn dou xn, and dou f2 dou x1 dou f2 dou x2 dou, so it should be f2. So it's some typo here. It should be 1 and it should be 2 and dou xn. And the last row we can write dou fn dou x1, and the last term we can write dou fn and dou xn. So this is a Jacobian matrix. So the dimension of this matrix n cross n, because the system we have considering the dimension n. So now let us define a function. Let us define a function if cap x equal to f star x plus fx. So here f star x is the conjugate transpose matrix of fx. Okay. So now, according to the Kaspersky theorem, if f cap x is negative definite, we can comment the equilibrium point which is xc, in this case it is origin, is asymptotically stable. Okay, so this is how we can come up the stability condition for the system defined by equation 1. This is 1. So now we'll formulate the derivations of this Lyapunov function for this equation, for the system defined by equation 1. So here the Lyapunov function chosen as v of x f star x and fx. So this is f of x is basically vector here. This is the vector. So here this is basically, it becomes the row vector if you take the conjugate transpose of the function f of x. So here also you're assuming v of x goes to infinity if x goes to infinity. So in this condition we can say the equilibrium state, which is origin, is asymptotically stable in large. Okay. So we are going to give the proof of this concept. So here we have chosen v of x equal to f star x and fx. One thing, this is the function actually, this is the function, and this is matrix. This f and this small fx, they are not equal. So now, if we take the time derivative of this v of x, we can get v dot x equal to f star dot x fx plus f star x f dot x. And also we know that f dot x, we can write dou f dou x dx dt, and from which we can write, so this is actually nothing but the Jacobian matrix, the dimension of this matrix n cross n, and from this we can write capital F of x equal to x dot, and x dot also you know that fx small fx. This is we are getting from equation 1. Right. So now if we substitute this expression f dot x here in the previous equation, so let us define, this is equation 1 and this is 2, substituting equation 2 in equation 1, we have v dot x, we can write f of x, and this is should be capital 1, so we can write capital fx f of x, this is star, in place of this part we can write, and into small fx, and plus f star x, we can write capital fx f of x, and from this we can take f star x, we can take common from the previous equation, so you can write f star x plus f of x to small x. So here what you have denoted for this function, this for this we have taken f cap x, this is here, this is defined here, f cap x, so we can write f star x capital fx cap and f of x. Now if this is negative definite matrix, then we can say v dot x will be negative definite. So we can write here, if f cap x is negative definite, then v dot x will be negative definite. Yeah, this is how we can prove the theorem. Now we'll take an example, we'll validate this concept. So example, so we have the nonlinear system x1 dot equal to minus x1 and x2 dot equal to x2 minus, sorry, this is x1, x2 and minus x2 cube. So from this system, we can easily find the equilibrium point. So here, so we can denote this is f1, x1, x2, and this is we can denote as f2, x1, x2, two functions. So from this, the equilibrium point, we can choose f1, x1, x2 equal to 0. From this, x1 equal to 0. And from second function, f2, x1, x2 equal to 0. And from this, we can write x2 equal to 0. If you substitute x1 equal to 0, so we'll get x2 equal to 0. So now, here, we can find, or we can say this is one of the equilibrium point for the system, one of the equilibrium point. There can be another equilibrium point. So now here we can now form the function f of x, we can form as f1x, f2x equal to, we can write minus x1, x2 minus x2 cube. So one thing I should mention here, here we are having also x2 minus x2 cube equal to 0. So x2, if you take common, minus x2, so we have 1 plus x2 square. So x2 equal to 0 from this, and x2 square equal to minus 1, x2 equal to plus minus I. So since we are considering the equilibrium point 0, 0, so we are, that's why you have taken 0 and x1 equal to 0. So now we can find the Jacobian matrix. So here we can form the Jacobian matrix from this fx. So f of x we can write equal to dou f1 dou x1 dou f1 dou x2 dou f2 dou x1 and dou f2 dou x2. Right. So we'll find the individual terms for this fx. So here we can find dou f1 dou x1 equal to minus 1, dou f2 dou x1 1, and dou f2 and dou x2 is 0, and dou f2 dou x2 it will be minus 1, 3 x2 square. Now if you substitute these terms in Jacobian matrix, we'll have minus 1, 0, 1, minus 1, minus 3 x2 square. Right. Now we'll find the f cap x, capital F cap s, which is defined here. So we can use this function. So here f cap x, we can write f star x plus fx, or we can write the transpose, conjugate transpose of fx, we can write minus 1, 1, 0, minus 1, 3 x2 square plus fx minus 1, 0, 1, minus 1, minus 3 x2 square. And from this, we can find the matrix minus 2, 1, 1, and minus 2, minus 6 x2 square. Right. Now we'll verify whether this matrix f cap x is positive definite or not. Also, we can write this matrix equal to minus, we can take common. So we can write 2 minus 1 minus 1. So it should be, it is, yeah, 2 plus 6. So 2 plus 6 x2 square. Right. Now we'll check whether this part is, this matrix is positive definite or not. So we can verify, you can use the Sylvester's theorem, and we can comment on the positive definiteness of f cap x. So first we'll find q1, what you have done before. So it is 2, this is positive, and q2, we can find the determinant of 2 minus 1 minus 1, 2 plus 6 x2 square. From this we can write 4 plus 12 x2 square minus 1, or we can write 12 x2 square plus 3. So this is also positive definite, because this we have the square term here. This is also positive definite. So we can comment f of x is negative definite, is negative definite. So if it is negative definite, we can easily find this v of x here, v of x, which is just simply from the function itself, we can find the v of x. So it's like the Lyapunov function, v of x equal to f star x and fx. This is f star x, we can form from this part. So we can take it common. And we can write here minus x1 and x1 minus x2 and x2 cube. And from this, we can write x1 square plus x1, x2 minus x2 cube. So this square. So this is our Lyapunov function for this system. This is how we can find the Lyapunov function for the system. And I hope it is understandable how we can find the Lyapunov function for the nonlinear system. Now we'll take another example to verify the concept. So here, example 2. We have the nonlinear system. Let's assume we have the nonlinear system. x1 dot equal to minus x1 plus x2, and x2 dot we have minus x1 and minus x2 cube. And study the Lyapunov function, or we can write, find the Lyapunov function of equation 1. So solution. So here we can form the function f of x, which is minus x1 plus x2 minus x1 and minus x2 cube. Okay. And we can form the Jacobian matrix. So I'm going to step jump process. I'm not going to the whole steps to find the solution. So we can find the Jacobian matrix f of x equal to dou f1, dou x1, dou f1, dou x2, dou f2, dou x1 and dou f2 dou x2. And from this, we can form the Jacobi matrix -1, 1, -1, -3x2 square, right? So here we'll find also the v of x. The v of x we can form as f star x into fx. Okay, this is our Lyapunov function to be designed. Lyapunov. But before we comment on the Lyapunov function of this equation, first we have to check f cap whether coming to be negative definite or not. So this is f star x plus fx, and from this we can find the conjugate transpose of f of x. So it will be -1, -1, 1 -3x2 square, and f of x we can write -1, 1, -1, -3x2 square, and from this we can find -2, 0, and 0, and 6x2 square, right? Yeah, 6x2 square, and from this again you can write minus, we can take common, 2, 0, 0, 6x2 square. So it easily can comment that this matrix is positive definite, this matrix. And since this is a negative sign is here, so f cap x is negative definite. So we can say, we can comment, hence f cap x is negative semi-definite. So now we can form the Lyapunov function, v of x. V of x we can form as f star x, f of x. So here f star x we can write I can take the original fx comma paste here, and we can write minus x1 plus x2 and minus x1 minus x2 cube. And if you multiply the row and column, we'll have the Lyapunov function, which is minus x1 plus x2 square and plus minus x1 minus x minus x2 cube whole square. So this is the Lyapunov function for the given system. So this Lyapunov function, through this Lyapunov function, we can check the stability of the system, of the equilibrium point of the system. So this is how we can form the Lyapunov function of any nonlinear system. This is the standard procedure to find. Here we are stopping the how and the Lyapunov stability analysis. And from the next lecture onwards, we'll be doing the control part. Thank you.